Uh, Hello, everyone. Nice to see you again. Today we have the first talk in the colloquium series this year. And first of all, I would like to acknowledge the traditional owners of Australian lands and pay my respect to the elders, past and present. Today, I'm happy to present Lou Lee, who is a professor and associated chair in Department of Physics at the University of Michigan. Lou is one of the leaders in strongly correlated materials, including oxide interfaces, quantum magnets, high temperature superconductors, and Kondo systems. Lou has received his PhD degree in Princeton in 2008, and after a popular fellowship in physics at Massachusetts Institute of Technology, MIT, he has joined University of Michigan in 2019. Lou has a number of awards, including Office of Naval Research Young Investigator Award and Outstanding Young Researcher Award from the Macronix Foundation. Okay, Lou, please feel to start and we will enjoy the talk.
All right, thank you guys for this kind introduction and for this wonderful chance to talk with you guys across the Pacific. I see some familiar names and I know many of you guys since conference back in old days before COVID. Anyway, again, I want to apologize for missing the starting time. Had a little bit difficulty as I'm doing this from home. But anyway, I'm going to try to keep it on time so I don't have to finish. And if you have any questions, feel free to just stop me and ask me. I'd rather treat this as a way to chat with you guys and discuss about physics I'm presenting here. Okay, so now let me just try to show my slides, see if that works. Share screen. Give me a thumb up if you see it. Thank you so much.
Works perfectly.
Here we go. All right, so here I'm going to talk about an ongoing long-time progress about a mystery of something happening in correlated insulator. Whether or not we have oscillations, quantum oscillations that's coming from Landau level quantizations in this narrow gap semiconductor. All right, the compound we're going to talk about coming from a mystery of Kondo insulator. Why and how there might be a different interpretation about the bulk gap and what happens to low temperature phenomena, the low temperature resistivity saturation, and the discussion about whether or not there's topological protection there. All right, and then I'm going through this as a long introduction, but a way to present you the dilemma we are running into where we observe something, but we still cannot understand the origin and how we treat the whole thing and give us a solution or a way to answer the questions as experimentalists. The compound, we're going to start with the well-known example, similar hexaboride, and then we will go to the compound that we find out turns out really work as the ytterbium dodecaboride or orbital. I'm just going to say the short names for this. All right, so bottom line is, once we finish discussion, we found something very puzzling. We find that the resistivity seems to give us a Fermi surface that's like a tube connecting between two large hidden Fermi surfaces in a narrow gap semiconductor or in this correlated insulator. And the phenomena, no matter what the origin we're going to conclude, it looks like a fermion. It looks like coming from fermion. That will be my conclusion. And again, I don't have to go exact to the last slides. I would love to have any of you raise questions during my presentation. All right. Okay, so these are really my wonderful collaborators coming either from the within University of Michigan or the wonderful collaborators providing us crystals. In this particular one, the important progress came from Professor Iga in Ikaraki University through my collaborator Yuji Matsuda. This growth of single crystal YB12 really helped solve the whole thing. And of course, the key players are my postdocs and students. Without them, nothing can be done. All right, let me get to the correlated insulator, or topology insulator business. So what are we looking at? I'm looking at a compound that has been known for more than 50 years. It's a compound of samarium, one of the rare earth elements, so going to a corner of this cubic lattice. Boron, B6, forms a cluster into the center of this cubic. This is a simple cubic lattice, and you imagine putting this lattice together, you have nice crystals like this. All right. If we look at resistivity versus temperature, it's just like typical semiconductor behavior. As you can see, as you cool down, the resistivity seems to diverge. But eventually, you have a saturation happening at a low temperature. That's a typical phenomenon that many groups got observed and got puzzled and debated since early days of 1970s. All right, let's put a little bit detail in that. In this particular device, we were able to polish and we were able to try to determine the bulk conductivity or bulk resistance. Now you see the saturation clearly from 20 or 30 Kelvin to base temperature. There are about 4 or 3 orders magnitude change of resistivity and then stop changing. So this activation suggests we have a small gap. And indeed, this is a correlation effect in the sense that we have the hybridization between the local F states and the conducting D states, and hybridizing give a teeny tiny gap. This gap is only in the order of a few or less than 10 MeV. But magically, the chemical potential at low temperature sits inside the gap. As a result, it turns into a narrow gap semiconductor, and that's where this activation behavior came from. All right. Of course, the question debates came asked about what's going on about the low temperature saturation, and there's many debates. Again, this is simple discussion about we have chemical potential right sitting in this hybridization gap, but what's going on about that low temperature saturation? Many debates. Eventually, now this is about 7 or 8 years ago, when my colleague brought me this idea of maybe there's a topological protection. As the way of opening a gap, hybridization suggests that there must be a band inversion. In other words, if the general picture that we believe happening to the bulk gap, there must be band inversion, and that band inversion is just like what happens in the typical topological insulator, bismuth selenide or bismuth telluride. As a result, there will be a topological protected surface state and outside the insulating bulk. And my colleague Charlie Kodak had this wonderful design of a non-local measurements for a 3-dimensional system. Typically for 2-dimensional system, we're looking for edge states, edge transport. In this particular case, their group designed something really going to from top to bottom surfaces and try to see what's going on. There's many analysis going through this, but for me as experimentalist, I just look at the data. What shocked me in the beginning was 2 different curves. One typical curve comes from the, let me turn into the cursor. Let me see, just a second. Oops, my bad. Laser point, good. It turns into a typical setup when you pass a current and try to measure a voltage in a typical four-pole method. Whereas the other one, trying to pass a current and measure hybridized way of voltage drop. So bottom line is this is a typical setup of one sample different configuration of full probe leads. For whatever reason, they start to give different temperature dependence. As experimentalist, I know that location of contacts may not be precise. So in that sense, we always have a scaling between the typical resistance of the sample to the bulk resistivity of the sample with a scaling factor, right? But these two traces, one is monotonic, the other is not monotonic. So clearly, there is a very strong anisotropy going on in this compound, in this simple cubic single phase crystal crystal. So that shocked me. But of course, my colleague worked with my colleague Kai-san. They figure out a way to model the transport as the surface conduction that's dominating there. All right, there's a surface conduction. Quickly, it's confirmed by the Irvine group led by Jinxia.
Could we interrupt you?
Yes,
I think there is a raised hand from Simonti. Please go ahead.
Yeah. Sorry, Professor Lee, I didn't understand how you measure the hybridization voltage.
Would you say a last few words? I missed that.
So how did you measure the hybrid?
Oh, excellent. This is excellent question. So very first, this is not my work, but let me just try to say that what my colleague tried to do, right? So there's a typical standard setup as you put the leads from the top to bottom and measure the voltage up from top to bottom. In this way, they just say that's a standard one. Then my colleague designed the thing of measuring either going from one way of putting current, measure voltage cross this way, or measure voltage cross the other way. That's, I believe, what they call the hybridized method. So what I'm trying to say is the following. There's a typical standard configuration like a way that I would do to measure a full probe resistance for a bulk. Then there's another way that looks ugly configuration that looks strange to me, but to my colleague, that's a way they find out they start to have a R versus T that look very strange, that's non-monotonic and quite different from the standard configuration. So I think that would be my way to explain my colleague's work.
Okay, thank you.
Okay, no problem, thanks. Yeah. All right, so actually, let me just say a few words about that. My colleague actually followed through all these discussions because this is way of doing the measurements of ugly geometry that I'm not familiar with. But later on, they started to use Corbino disk geometry when it's actually way straightforward to think about whether we measure a top surface or bottom surface. And then they further designed a way to measure a reverse Corbino disk geometry to determine exactly what's the conduction is in the bulk. And I would encourage you guys to look for the work and work following that to really see that how they design these configurations to for this detailed fancy electron transport configurations. Again, this is not my work, but I was really impressed by how much electronics development they put into to measure a divergence of a bulk conductivity or bulk resistivity by 9 orders of magnitude. This is some work followed by my colleague Charlie Kodak for quite a long time. I'm also going to say that for this conduction check, for the surface conduction check, Jinxia group from University of California in Irvine did this similar test, but chose a sample that looks exactly like a wedge. And in this way, they try to measure the electrical Hall signal, right? As you pass the current from one side to the other side. And clearly thickness stays, well, the other geometries stay the same, but thickness are different for all these geometries. And to the surprise of the community, the Hall voltage does not seem to change with the thickness. I think that's what also supports a surface conduction happening in this compound. Finally, quickly within that time, the Maryland group led by Professor Pogolian tried to determine the bulk gap through the point contact spectroscopy, and they also confirm the bulk gap. These three work really open the field. All right. Okay, so let me try to say that what motivated me, right? We know about the surface conduction, and quickly there's this non-local transport, photo emission to show the direct dispersion, photo emission, the STM, and later, including my group, the quantum oscillation. But all I'm trying to say that from early work, we know there's conduction, and yet we did not know the surface state, orbital size, or geometry, right? And how do we know this geometry? We go from quantum oscillation. And a quick tutorial about what we do with that, nothing surprising. We learned that having a magnetic field, there will be Landau level quantizations. So this quantized orbits would start to split the energies, and we have the Fermi level that's going into the maximum of the denser states, or minimum dense states, or maximum dense states as we increase the magnetic field. In this way, we have high, low, high, or denser states. As a result, the electronic property or magnetization or so on and so forth will oscillate as a function of magnetic fields. So that is quantum oscillation. And further, a detailed study showed that this oscillation pattern turns out to be exact periodic in 1/b, and that period, as you can see, that this is just an example of the copper doped selenide, this periodic pattern in 1/b, and that oscillation frequency turns out to be proportional to Fermi surface cross sections. That's how we would know the geometry of Fermi surface, just by looking at how the orbital sites change as a function of magnetic field directions. For example, if we have a Fermi surface like this ellipsoid, right? Well, how do we know the Fermi surface like ellipsoids? We have a magnetic field, we get the maximum minimum cross section, right? And then we turn on rotations. When I talk with students, we always argue that this is just like big knife. Imagine that we have a watermelon. Imagine we are ants living on surface of this watermelon. How do we know watermelon looks like a watermelon, right? We would try to measure the cross section. Just imagine that just like a field. In this way, we have a big knife that slides this way and look for a maximum, cut it. We look at this and we find out a circle, and we find out this area, right? Imagine we rotate the magnetic field, or we rotate how we cut this watermelon. This way, we have this area. This way, 45 degrees away, we would look at an elongated ellipse. If we cut horizontally in this way, or magnetic field cutting in this way, means field perpendicularly, we would have an ellipse like that. So basically, this is the way that we can map, we can see what's going on with the Fermi orbital size, and we can understand eventually how the Fermi surface look like inside the metal. Okay, all right, enough tutorial, right? I was shocked by the progress in this interesting correlated insulator. I knew that something would happen to have a strong magnetic field. This is my research. Yes, please.
Interrupt you. So could you return 2 slides back? I think one slide more. When you show the results, they were shown for the magnetic field that is applied to the surface. Do these oscillations persist when when magnetic field is parallel to things?
This is an excellent question. This is an excellent question. Back to your question, it's a question that the answer depends on the exact compounds, whether there are 2-dimensional compounds or there are 3-dimensional bulk compounds. But this is a question that eventually we will see that answers that what the geometry we're going to have for this interesting system. In this particular example, copper doped selenide, which is a topological superconductor, is heavily doped after selenide. It turns out we actually observe quantum oscillation as we have a field in plane, which means this compound, the firm surface, at least my compound, the firm surface is a three-dimensional firm surface with the elongated ellipsoids, right? In this particular compounds, there are still debates about in what level of copper doping this closing of firm surface would go and turn into orbits, which means we're going to have no oscillations. And that's a different topic of interesting discussion there. I'm not going through that, but you raised a wonderful wonderful question, because for Samara Hexford, that's a big debate.
Okay, thank you.
Yeah. All right, now thanks for this wonderful questions. But basically, we have approach. We thought we'd do something. We thought we knew something would go on. And we just need to carry out strong fields and try looking for oscillations out of that metallic surface, right? And they say this is topological protection. We should do something, right? And yet we got the best device, best Hall bar, in this case, actually best Coulomb disk geometry device, right? We went to the strongest DC magnetic fields on Earth. This is Tallahassee, Florida, when we were able to go up to 45 Tesla, had a few failures in the magnets, but eventually runs, we go up to 45 Tesla, nothing happened. We were really disappointed. My students were really disappointed. My postdoc were really disappointed. Well, what we can do in the beginning, right? I told them the life in a lab always sucks. No matter what we do in the beginning, there's always a failure. So to start with, we had resistance measurements. Nothing seems to happen. Nothing seems to show us quantum oscillations. But we knew that the fundamental quantum oscillation should come from thermodynamics or magnetization, which is something directly proportional to tensor states or proportional to the change of free energy. Because from Jackson, we know that magnetization is nothing but dFdB, right? So the question, of course, is at that time, we thought it's coming from surface states, and immediate question is how would we measure the teeny tiny volume of surface? So we decided to measure magnetic torque, just like how we align the compass. We have a field, any dipole moments would try to follow the magnetic field directions, and that's a result of magnetic torque, M cross B, right? So that's a simple principle, and the design is quite straightforward. We have a sample sitting on a floppy cantilever. Apply magnetic field. If there's anisotropic response, that means we're going to generate a torque, and that generation of torque would deflect the cantilever, and that deflection would turn the cantilever, and from that we can calibrate and know the torque and know the effect of magnetization. Let me also emphasize that I'm measuring a torque, M cross B. That means that I have to have an anisotropic response. If it's complete isotropic, nothing will happen, right? So that turns out to be a way to measure the perfect, to really select the response that's get emphasized by the elongated firm surfaces. So this is a principle. This is a simple picture of the design. This is not Samara Hexford. Samara Hexford is much smaller than this, but it's a very early picture that I took during my graduate school studies when I have a bismuth sitting on a floppy cantilever, and the cantilever is standing up. I have a small gap between this metallic cantilever and a gold film underneath. So I have a teeny tiny gap there. And then I have two metals that forms a capacitor. And by tracing the capacitance and magnetic fields, I know the deflection. All right. So this is a capacitance, and we were able to trace the capacitance down to about a part per million level, which translates to the part per million level, or this about sub-millimeter difference, which translates to sub-nanometer change. So that's how we knew the deflection, and it gave us a good resolution that's many orders of magnitude better than commercial available magnetometry. A very quick thing that this thing is very easy to adapt, and to show that I'm having this setup sitting on a piece of penny. Well, this is actually a question I should ask the audience. In US, we still use penny. How about in Australia? You guys still use penny? So when I give this talk to some audience coming from, for example, from China, or from maybe even from Japan, they do not know what a penny is, because it's just too small unit for them now. Anyway, so a piece of penny.
I would call them cents. But
Okay, yeah, okay. Anyway, you guys know how small a cent is, right? It's a typical centimeter, sub-centimeter setup, right? So that's how we can show. Well, this is a way to show a typical size of setup. Well, it's also a way to show you guys how cheap we are. We just make tons of this kind of level to fit the need of our collaborations. And it's easy to make. It's just straightforward capacitance measurements. Means that as long as we have a probe with the good coils cables, we're able to adapt. That's how we adapt to 45 Tesla for this particular study. Or now these days, it's up to 60 or 70 Tesla in Los Angeles, where we're able to use their probe to go to pulse field facility for the capacitance measurements and eventually for the magnetization. Okay, enough about setup, and we were using our own fridge, or most of data here presenting will be using the hybrid magnets. This is in Tallahassee, Florida, the high magnetic field lab. Okay, so what do we expect to observe? We're going to look at a paramagnet to start with. Paramagnet to start with, that means M is proportional to H, so it's just from the polarization, right? The torque, which is M cross H, linear times quadratic times linear, right? We will have a quadratic dependence. That's typically majority of compounds going to show at a very low field. Turns out that's indeed what we observe out of this compound. It's a paramagnet. All right. And we emphasize once quantum oscillations start to show, we should observe oscillation pattern on this. And for summer hydroboride, let me quickly go through my data, and you will see that where dilemma comes from. We will look at this simple cubic structure with top facets, edge facets, even facets coming from 011 plane, which means top edge facets, or a 011 plane facets. So we have 4 of this family and 4 of this family as we rotate from one primary axis A to the other primary axis C. To make it clear, we just now this is side view. As you can see, we rotate within this plane. We have 2 families, each contains 4 planes. All right. Okay. That's how we do, and this is our very early data when we look at magnetic torque versus magnetic fields. As I talk about, at low fields, it's a quadratic, it's a paramagnet. As we go stronger field, 5 or 10 Tesla, we start to have these wiggles. We even have some slow wiggles and fast wiggles, which means that there's a lot of things coming out as we try to measure the magnetic torque. Now, that's magnetic torque. We divide the torque by H to get our effective magnetization. And this is data we present all the way up to 45 Tesla. And low fields, again, we have this linear dependence, nothing surprising. This is paramagnet. As we go to stronger fields, we have slow oscillations, fast oscillations, or beating pattern, or that fast oscillations. That means we should have at least 3 primary frequencies. And indeed, we have 3 primary frequencies as we carry out field analysis to know the oscillation frequencies. All right. So without going through the detail of this is basically our spectrum. And we carry out this in many, many different angles. And we emphasize, we turn the angle, we're looking for the oscillation frequencies, and we try to trace them. I know this is complicated to go through. Let me just try to see that how we track through this. As I talk about, we rotate within this plane. We can look at each side of this plane and see how they evolve. One particular thing that we look at this involvement, and we find out the minimum happens about 45 degrees here. And we talk about that would be exactly when the field along this primary axis, actually not primary, 011 axis of this, It's either coming from these surfaces or just from elongated ellipsoids or cylinders along this axis. All right, the other sets and the other sets. So we have out of this family, we further out have the dispersion out of this family. So one set, another set, again, minimum happen about 90 degrees, which means that we know this is these orientations marked by these two surfaces. All right, and this sets. Okay, so basically this is our quick view about what we observe. We find out one set of peaks will have minimum exact and 0 degree, and we say it's gamma. Back to question Dimitri raised, right? We because of the fact that this is a ball crystal, we have surfaces coming from all the orientations, right? And we can only look at each branch and see how they eventually diverge. These diverge, eventually we will not be able to observe that because it will be gone. But because it's from neighboring facets that's 90 degrees away, we will still have the oscillation in those angles just coming from different branch. This is coming one set. The other set, it's actually coming also follow the dispersion of sorry, I forgot to mention, this is a 1 over cosine angle dependence with minimum here at 0 and 90 and 180 degrees, whereas the other is from 45 100 at 135 degrees, which means that, as I emphasized before, it's a cylinder-like Fermi surface with minimum happening exactly in the other family of the facets. And slow frequencies, again, building up statistics, we have that again coming from 0 and 90 degrees. Anyway, this is what we have been saying in oscillation pattern out of the very early example of Kondo insulator seminar hexafluoride. Before I go into the discussion controversy here, I'd like to hear if you guys have any questions.
Do you have any questions? Please just go ahead.
All right, okay. Now, this was about 8 years ago. We were exciting, but we find out, so what? This is a correlated insulator, right? And we showed something like, looks as if bismuth selenide, right? We have surfaces now coming from different facets. We know it's single crystal, cubic-like single crystal. So we'll find out something like a Kondo insulator, right? But quickly,
could I interrupt?
Yes, please.
Is it so? Feeds a picture of the 3D. So it is a bulk probe.
True.
Or could it provide any information about the surface states?
This is an excellent question. Let me actually comment things by bringing the wonderful work coming from the Cambridge group, right? Okay. This is argument that many people raise quickly after our work. We use a bulk probe. We have something that look as a bulk probe, and from the fact that we see that our data show they follow the 1 cosine angle dependence, right? We know, what do we really know? We know the dispersion supports a cylinder-like Fermi surface. There's no dispersion along that particular direction. That's what we know, right? Based on the data, it's like a cylinder, right? Now, the only way that we can argue is coming from surface is the conventional wisdom combining with have seen a very good insulator with a Kemp potential exact inside that energy gap. And combining these two, we thought we saw observations from surface states. But as experimentalists, the data itself told us that this is cylinder-like Fermi surface. And in early days, people would just say this is two-dimensional Fermi surface because there's no KZ dependence. Now, within a year, the Cambridge group led by Professor Sujitra Sebastian observe pattern that I would argue similar, but they may say that's something quite different. Basically, we observe the pattern in this range, where in similar range, they also observe this nice pattern. What's different is we use a cylinder-like firm surface, where they find out their data fits best with elongated firm surface, elongated ellipsoid. In this review article, we compared our data with their data, and we believe that within the uncertainty, our data below kilotesla are pretty much consistent. Model is different. We use a cylinder, they use elongated firms, elongated ellipsoid. That's a difference there. So to us, that raises the interesting question that if it's indeed 2D or 3D, in particular, their samples also showed oscillations that's way bigger than what we observed here. Here it comes into 10 kilotesla range, when the oscillation frequency here is in a range comparable to copper, gold, or silver, all these noble metals. That's what our sample did not observe. And unfortunately, we were not able to confirm that. But if that's indeed the case, there's just no debate that that's definitely a bulk phenomenon. Okay, but that's important question. As you can see that my data supports this type of firm surface, but that can still be a bulk or surface.
Can I ask a question, sorry?
Yes, please.
In your picture on the left-hand side, bottom left,
Right.
if your Fermi surface really was a cylinder, wouldn't you expect this to go down to 0? This frequency amplitude? Instead of a finite minimum, would you expect it to go down to 0 when you're...
No, the reason is if you look at this cylinder, right? I still always have this smallest cut as we have a field exactly parallel to the primary axis of that cylinder. That minimum cut, actually, yes, for this cylinder, that minimum cut is just this belly.
Ah, okay.
Right.
And then when it goes up to infinity.
Right. But you're exactly right. If I have a field 90 degrees away, I would see divergence of orbital sides, right? But my oscillation amplitude would quickly diminish because that very first orbital size is too large, and then there's not much field really projecting into effective field. So we quickly diminish. So in other words, that's why our error bar is getting bigger and bigger, because oscillation amplitude is getting smaller and smaller as we go field along this axis.
Okay.
Yeah, that's a wonderful question. Okay, all right. So now let me say that this is a mystery. Let me skip that. There was some further work of polishing, and we were able to resolve the issue, but start seeing another issue with hysteresis. But let me just quite quickly go to the discussion and see that how we approach this problem. There are many proposals coming out of this dilemma. When we see oscillations in an insulator, there's this very interesting exotic behavior arguing from whether it's exotic pattern like a spin-on Fermi surfaces or field superconductors, or something a little bit more conventional when they argue something like in disorder-driven states, there's something field in the tensile states, whether it's coming from the free energy oscillations or coming from these states. There are many interesting proposals from theory. As experimentalist, I want to be quick, but I want to show how we treated the thing, right? Very first, the challenge we have to answer, are they coming from bulk or surface, right? The thing that we need to do, as many theorists suggest, that we need to do the control experiments, which means we have to have a sample. Let me show, let's say, suppose we have to have a sample this way, right? We have to cut the half, measure again, cut a quarter, measure again, and see if the oscillation amplitude scales with that vanishing volume. That project turns out went nowhere, because we can never consistently get back to the strong magnetic fields without any change or conditions each run. That's every half a year. But we what turns out, we were able to look at a control experiments by luckily finding out an ugly sample that looks like this. In regular sample, it has it has the shape that some facets are really large, some facets are really small out of this 110 facets. And we confirmed oscillations down to very low temperature, and we confirmed oscillation frequencies. And just looking at this set of facets, again, one of cosine angle dependence out of this red, one cosine angle dependence out of this blue, right? The orbital sites follow what's expected out of crystal symmetry, four-fold symmetry, because this is a cubic structure, nothing's to change to its electron states. Whether it's bulk or surface, the orbital sites stay the same. One direction versus the other direction. What's
Could I
yes.
have a question? Could I
Yes.
interrupt you? So, so I think the important fact that surface states don't have just one Dirac cone, but they have 3 Dirac cones, and two of them are displaced in energy.
Right.
So in some sense, when you cut, you have not just one watermelon, but one large watermelon and one small. Does it mean that when you address oscillations, you're supposed to have 2 periodicities given by the size of large and small watermelons?
That's an interesting thoughts. I never going into deep into that to see that how the polishing or cutting starts to alternate orbital sites, as we never succeeded getting consistent results, right? That's let me think about that. That's something quite interesting. I have to think about how to address that, right? All I'm trying to say that we did not get too far with this idea of cutting, polishing, and coming back. But we did try to get one sample and look at the oscillation amplitude, orbital sites or oscillation amplitude in different orientations. Here, without doing all this work, we show that it follows what's supposed to do, the crystalline structure, cubic structure, so that every 90 degrees, I should repeat the pattern. But what shocked us was once we look at the oscillation amplitude, it turns out they seem to favor one direction than the other one. Red is larger, way larger than blue, which is 90 degrees away just from another family of the same crystalline symmetry.
Okay, thank you.
So that's really positive, right? Now, if everything is determined by the simple bulk, right? How would we have a large oscillation amplitude which suggests a lower disorder level along one axis? Then the other one would be more disorder. Why would disordering have orientation preference? This way is better than the other way. That made us still hesitant to think this is a completely bulk phenomenon. Is that 100% surface? That's another big puzzle. The big puzzle indeed came from this, right? Imagine this is 100% from the surface, just like this. I see no way that would prevent us to make a full probe leads to touch this surface and try to resolve the oscillations of the electron transport of this surface. That's another big puzzle, but that's also an important question. We failed in the beginning and we're still feeling about getting oscillations in electron transport of similar hexagon or SMB6. But still, this is a big challenge because whether or not we observe that oscillations in electron transport, that tell us to the first order, are we seeing a charge process or charge neutral process, right? No matter what's going on, if we can never really see oscillations in electron transport, we may have to consider this is really a bulk phenomena with a charge neutral process, maybe given by boson, for example, right? As many interesting proposals came from. But as experimentalist, I would never think about never. I know the compound SMB6 field, but we may try some other Kondo insulators with either narrow gap or lower gap closing fields and see what happens. And since I'm running out of time, I will just quickly present the observation. An observation is SMB6. We find out the maximum field, 80 or 100 Tesla, is not doing anything. Actually, a few weeks ago, there was evidence suggesting even 180 Tesla is barely closing the gap. So we do not have magnetic fields in this range closing the gap. But for another compound, WebB12, early data already suggests 45 Tesla. This is kilo study, which means there's a 1:10 ratio. Basically, about 45 Tesla, we're able to close in the gap. And indeed, we were able to find these crystals thanks to collaboration from Matsuda's group, from Professor Iga. And we look at electrical transport resistivity versus temperature. Again, it just looks as if a typical Kondo insulator like SMB6, from room temperature to base temperature, I have almost 5 orders of magnitude divergence of resistivity and the saturation, just like what we saw in SMB6. And when we look at this semiconductor-like behavior, even up to 45 Tesla, I'm still have this semiconductor behavior, like 2 order magnitude change, just from 3 Kelvin downwards, right? And yet, in the field range below 45 Tesla, when we look at magnetic torque versus magnetic field, we have this nice size of wiggles in magnetization, which is again repeating what we have observed in SMB6. Magnetization shows oscillations, right? Now, when we look at resistivity, finally, we observe oscillations in the raw data, resistivity, resistance versus magnetic fields, and we have this nice size of wiggles. It's a charge process. And even more, we can start to look at the temperature dependence. This is the magnetization, and we look at how warming up the sample reduce the amplitude, which is nothing surprising. This is the behavior of fermion. This is what we expected out of the Fermi-Dirac distribution. The temperature dependence, this typically called the LK formula, is simply derivative of Fermi-Dirac distribution, and torque shows this follow that trend, and resistivity also follow that trend. Let me emphasize they follow this trend, give a really heavy mass, right? In early data, based on the data directly, we have this difference between the effective mass. Our latest work, when we look at the resistivity oscillation normalized not by the zero field resistivity, but by the background resistivity, it seems to give us a consistent mass. And I would encourage you guys to look at our latest work to see that where and how that seems to give us consistent mass in the order of 7 ME. All right. But bottom line is whether or not it's fermion, whether or not what origin would be, I find out it's gonna be a fermion because the temperature dependence is so straightforward. All right. The angular dependence is puzzling, as I emphasized. Some torque data gave me something like cylinder-like Fermi surface. Maybe cubic, but whatever, that might be the good fit. But bottom lines for resistivity, SDH oscillations show that it's like a hyperbolic dependence, which means I'm having a narrow neck that's touched by 2 hidden Fermi surfaces. That's very strange, and tell us that if we do something really well, we may even be able to observe that hidden orbital size. Right. Okay. Let me quickly go through here, and we see this pattern, and our collaborator Matsuda's group observe that there is some finite thermal conductivity intercept that suggests there's a thermal fermion, even though the bulk itself is electrical insulator, right? And we push the magnetic fields even further, going beyond 45 Tesla. When we're able to still observe oscillations on the bulk conductivity, we start to have a contrast between the bulk phenomenon, between the insulator and the metal. Let me quickly do this contrast. Below and low fields, is an insulator, transport-wise. And yet, resistivity shows the oscillation and follow exact linear trend in this Landau level fan dependence, right? Here in strong field, it's a metal, but it's a metal when we look at a Landau fan, it's strongly nonlinear. A metal shows a very strange nonlinear pattern, whereas an insulator shows something just straight line. Again, that's big contrast, and seems to suggest that whatever happens inside this sample, this something is very different from what happens in the metallic states. And let me quickly go through here. Let me just skip this. Let me just stop here, and I'm happy to answer your questions. Thank you.
Thank you for a very nice talk. Please go for questions. Please just go ahead.
I had a question. So your oscillations, you only ever see oscillations when you're in this plateau part of the resistivity, the temperatures within the plateau?
Yes, you're exactly right.
And they're killed, their oscillations are killed when you, as soon as you go higher above the plateau.
That's a good question. My answer would be that not exactly in the following sense. Maybe it's easy to look at the temperature dependence. So look at temperature dependence. My resolution tells us eventually about 1.1 or 1.5 Kelvin-ish for both samples. I'm not able to resolve much oscillations, right?
Mm-hmm.
So back to the transport phenomena, that means it's roughly around here.
Okay.
To say that, but you see that this is not exact plateau like what a quantum plateau is, like quantum Hall plateau is, right? Because in this logarithmic plot, it's still increasing slowly, which means it's a much weaker divergence of resistivity, but it's not exactly flat. Right. So back to your question, are they correlated? My gut feeling is they're not, because whatever happens here is still a few kelvins above whatever my vanishing of oscillations is. But the question still remains, right? I think that's a mass behavior, but you may argue that what if sample is super clean, that we may still be able to see quantum oscillations at 5 Kelvin or 10 Kelvin. If sample is super clean, means that mass is damping but not killing everything. Now, gap is still finite or gap is vanishing. Are they going to change Fermi surface topology, or are they going to completely change the phenomena kills everything? That's a big question, and we do not know. We don't have that sample yet. We don't have a sample clean enough to tell us anything interesting yet above 1.5 Kelvin for this particular compound.
Okay, thank you.
No problem, thanks.
Any other questions? Please just go ahead. I have a question. So from the theoretical perspective, this ytterbium boron, is it also a topological Kondo insulator?
That's excellent question. This is a very interesting question. Back to your question is, indeed it is. And it is in the sense that the early prediction or early band structure calculations eventually show the gap opening, and they argue that it's not exactly time reversal symmetry protected, but protected by the crystalline symmetry. In other words, they believe this is topological crystalline insulator. That's from the theoretical prediction. On the experimental side, photo emission actually identified the surface state with the odd number of Fermi surfaces, which actually support this is actual topological insulator and zero field. Okay. So there's still some difference between the band structure calculation and the photo emission study.
Okay, thank you. Any other questions? Please just go ahead. So I have another question, I think more general one. So from the theoretical perspective, there are two models, the periodic Anderson model that use electronic language. And I think most of the interpretation uses it, but there is an older version. It seems to me it calls the Doniak model, when you have electrons coupled with a periodic lattice of spins, that you have these magnetic moments. Haven't been tried to address from this perspective, because you already have magnetic moments built in the system, because it is a Kondo insulator.
Right. Again, as experimentalists, all I can say that different approach from theoretical sides are very interesting. I'm not qualified to exact answer that, but I can offer my perspective, right? I'm looking at, or many of us are looking at typical Kondo insulator, which means we have more number-wise or density-wise, more electrons than the local moments, right? That's a Kondo system, right? Professor Emily Morrison from Rice actually found compounds that there are more magnetic moments than the carriers. That's exact opposite of this limit, and that's where, well, they argue that's they name the thing as a Kondo exhaustion insulator, right? So that's opposite of Kondo phenomena. But question actually remains that if we are still going to see quantum oscillation in the opposite limit of a Kondo problem, right? Again, I don't quite understand or quite know how to address your question, but there are experimental efforts to go through the other opposite and see what's going on.
Okay, I see. Thank you. Do you have any other questions? Please just go ahead. Let's wait a few seconds. If there are no of them, let's ask Lou again. Thank you for fantastic talk.
Oh, thank you so much. Again, I really apologize for the for late response all this issue, but I really appreciate your effort, and this is wonderful. Thank you, guys.
Very interesting story. Yeah.
All right.
Okay. Bye to everyone.
Yeah. Bye. Thank you.
See you in a month.
Bye-bye.
Bye.
Yeah. Bye, everyone.